I bought a cheap optical spectrometer in the Chinese online marketplace, Taobao. It only cost me $49, so I guess that makes it a ridiculously cheap spectrometer. For sure, this isn't a lab-grade instrument, but I have found it to be really bloody useful. What I'm going to do is review the product, test it with a wide selection of light sources, and even perform a teardown. The whole reason I bought this spectrometer was to validate the wavelength of some of my ultraviolet flashlights. For that application, the product performed flawlessly. Later, I wanted to try and figure out the gas mixture of some ionized Geiger-Müller tubes. So I used this cheap spectrometer to look at the emission spectra from each of the tubes, and to my real amazement, I was able to figure out what gases were used in each one. In my video about the experiment I was doing, I received a lot of interested comments about my cheap spectrometer. So I figured I would review it, test the crap out of it, and let everyone see if it stands up to scrutiny. So here goes. Some of you might be wondering why I didn't just build my own spectrometer. I am an engineer after all. There are three basic reasons that I feel that it is pertinent to mention. The first one is that I have built a basic spectrometer before, albeit for our kids to use and learn from. But, to be honest, it wasn't anywhere near as good as this device. The second point is that there are literally hundreds of really good YouTube videos showing the process of making DIY spectrometers, so I didn't really see any value I could bring to this already crowded space. But really, the most important reason why I just bought one is that this particular one is far better than most of the DIY projects on YouTube. It works straight out of the box, and yet only costs $49. I should probably mention that this device was not produced in a factory. It is a DIY project from an enthusiast who has built and sold about 200 of these things. You will be able to see more about that in the teardown later in this video. Quite a few people who watched the last video were wanting to purchase this device. I have also been in touch with the person who makes it. Later on, I will let you know what I am doing to help people purchase this spectrometer from outside of mainland China. The spectrometer comes with its own calibration light source, in the form of a compact fluorescent lamp. This lamp has very specific emission lines, determined by the types of phosphor used in the bulb. This makes the calibration process completely seamless. The device also comes with some light diffuser strips. These are really helpful when measuring bright point sources. You can see here, using 365 nanometer ultraviolet light, the diffusers are still able to transmit some of the rays, although clearly, there will be some reduction of the overall intensity. This spectrometer doesn't ship with any software. There is freeware available for this, and I have used the Theremino software throughout this video. It certainly isn't the best software around, but it is probably the easiest to use. Spectragryph is another one, but this has a steeper learning curve. To test this device, I am going to be using a whole lot of different light sources. In fact, this is a story that is best told from the point of view of those things that are being used to test this spectrometer. I think it is a lot more interesting way to show what it is that this product can actually do. Okay, let's test this sucker. The first light source that needs to be tested is the compact fluorescent lamp that was supplied with the spectrometer. This is used to calibrate the software, and the tube that was included has a number of known fluorescence lines from the phosphor coating on this model of tube. CFL tubes are just a standard mercury vapor strip light that has a built-in electronic ballast and starter circuit. Being compact, they were a great drop-in replacement for standard incandescent bulbs. The calibration process is really straightforward. Just drag the trim points for 436 and 546 nanometers to these two peaks, and the process is done. It's only a 2-point calibration, so expect some errors in the ultraviolet and infrared parts of the spectrum. Although CFL lighting is much more energy efficient than incandescent bulbs, you can see here that there is still a lot of heat released in the operation of these devices. This is a raw mercury vapor arc lamp. This one is sold as a UV sterilizing light source. It is essentially the same technology as used in the CFL, but it doesn't have the fluorescent coating on the inside of the tube, so the ultraviolet rays that are generated are able to leave the bulb. UVB and UVC rays are dangerous, so I always wear protective goggles designed to filter out ultraviolet rays whenever I use this light source. What I can tell you about this potentially dangerous light source is that despite the hazards, it produces a rather interesting light show. The startup process in particular is quite hypnotic, and like most things, no camera can truly capture its beauty, like the human eye. At UV, there should be lines at 365, 254, and even 185 nanometers. Basically it should have narrow emission lines at UVA, B and C. On this spectrometer, I can only see the 365 nanometer line. What I don't know yet is if the others are present and not detectable, or if the glass envelope of the bulb is blocking these emissions. I'm going to use some test cards to figure that part out. The larger of these test cards has an area that is only sensitive to UVA, the other has a UVC detectable strip. As you can see, there is certainly some UVA detected, but from this camera angle it is not clear if there are rays present from the 184 nanometer UVC line also present. In this demonstration, it is far clearer. For sure there are UVC rays present, and I need to be careful, both for the sake of my eyes, and also I will limit the exposure to my skin as well. The glass enclosure of this bulb is clearly able to pass UVA, B and C. So far, I don't know the upper energy limit of the detection range of this spectrometer, but it seems to be between 254 and 365 nanometers. We can figure that part out later. What I do want to show you first is how this bulb is related to a standard fluorescent strip light tube, like this. I am going to very carefully open up this tube and extract some of the fluorescent coating. I have wrapped it in several layers of polythene bags, and now I am ready to apply a precision tap to the delicate glass tube. I collected some of the fluorescent powder from the inside of the glass, and placed it inside a sealed bag. When I wrap this around the tube, you can see that the visible brightness of the light actually increases. This is because some of the invisible UV radiation is now being converted to visible light. When I was young, the principal form of domestic lighting was in the form of the humble incandescent lamp. At its heart, it is little more than a heated metal wire, but this description hides the subtle technology, and the century of painstaking hard work, that has gone into the modern version of this light source. Incandescent light bulbs are seldom used today, the energy efficiency is just too low. The light has a spectral content that is biased towards the red end of the spectrum, and this gives them the characteristic orange hue. Much of the light that is produced is infrared, and so, completely useless for lighting purposes, as it is invisible to the human eye. In a previous project, I bought a long pass filter. This is used to filter out everything except the infrared part of the spectrum. I used this on a DIY night vision system that used a cheap webcam. A link to that project is in the description below. Here, you can see just how much of the light emitted from this bulb is invisible infrared rays. Now, I am going to filter out the infrared part of the spectrum, using a short pass filter. I took this filter from a lens that was used in my night vision camera project. I had a feeling that it would come in handy. Some of the red light has also been removed by this filter, but in general you can see just how much of the emitted light is wasted. And not only is energy lost to near-infrared, but also to thermal infrared rays too. Here you can see on the thermal camera, just how hot this incandescent lamp gets. I want to take a quick look at the optical spectra of one of the most common light sources in the world, LEDs. I got this cheap box of LEDs to test with. First of all, I want to thank my kids for making this convenient test board for the LEDs. The first LED is described as being light green. This gives a single line at about 575 nanometers. The emission line isn't as narrow as a laser, but it is quite monochromatic. The spectrum of a white LED is created in a very interesting way. This process has more in common with fluorescent strip lights than you might think. There is only actually a single blue LED inside this device. The green, yellow and orange components that you see here are created by a mixture of fluorescent materials placed in front of that LED, and emit these wavelengths when excited by the blue source. There is also a significant infrared peak at about 905 nanometers. I assume that this is from a secondary peak from one of the fluorescent materials within the illumination screen. I also assume that more expensive white LEDs will filter out this unwanted infrared radiation. Red LEDs are a lot more simple, just having a single line at the emission wavelength. The orange and the dark green LEDs are also similar, in that they only give a single line of optical energy. The energy of these emitted photons is determined by the bandgap energy of the semiconductor within these devices. This next LED is labeled as being pink. This is basically the same as the white LED, but just has a different mixture of fluorescent materials within its illumination screen. The blue and yellow LEDs are again just basic LEDs with the bandgap tuned to each of the required wavelengths. This next LED is described as being purple. This appears to use an ultraviolet LED to stimulate fluorescence with a violet color. There is also a very strong secondary fluorescence line, in the infrared, at about 780 nanometers. This amount of infrared energy being emitted is quite concerning, but nowhere near as problematic as the strong ultraviolet radiation that this LED also emits. I will make sure that the kids don't get to play with this particular LED. This is a special type of incandescent light source, called a halogen lamp. It is able to operate the filament at much higher temperatures, due to an effect, called the halogen cycle. As the tungsten atoms are boiled off the filament, they are redeposited back on the filament in this chemical process. The higher temperatures give rise to higher energy photon emissions. Although at first glance, the spectrum might look very similar to that of the standard incandescent lamp, there is actually a lot more blue light present. I obtained two different types of halogen lamp. Outwardly, they look almost identical. One is a very low-cost bulb, intended for domestic lighting. The other is a lab-grade product intended for spectroscopy and other industrial applications. As you can see, it clearly states that this device is not intended for home use. There is also a warning that this lamp will generate ultraviolet rays, infrared rays, and that it should not be viewed with the naked eye. Using a spectrometer like this is a great way to find out what the difference is between these two types of lamps. although on camera, there is very little difference between the visible color of the two lamps. To the eye, the lab-grade lamp appears to have a whiter light. Looking at the spectra, a number of things become obvious. Firstly, the lab-grade lamp has a significantly wider spectrum. It is also clear that both lamps produce both ultraviolet and infrared rays, but the lab-grade product has a lot more of both of these types of invisible light. Having such a wide spectral continuum makes halogen lamps great for testing some optical filters. I had these filters left over from a customer project I worked on some time ago. Let's see what these things do. The first one is labeled as a 500 to 700 nanometer filter, but I can't remember if it is a bandpass or a band-stop filter. Okay, so it is a bandpass filter and it has a very nice sharp response. The next one was labeled as a 560 nanometers filter. I'm pretty sure that this one has a narrow bandpass characteristic. And indeed it does, and with a very narrow passband. The next one is a 1064 nanometer infrared bandpass filter. As you can see, there is a lot of noise in this measurement, due to the light being far less intense at this wavelength. It is interesting to contrast the sharp responses of the filters designed for scientific and industrial applications, with those that are intended for consumer use. This filter set is designed for use with a flashlight, and has red, green, blue and infrared filters. I'm going to set the Theremino software to use the unfiltered halogen spectra as a reference, and then measure the filter responses with respect to that. The relative response of the blue filter is pretty lousy, when compared to the filters I previously tested. The green filter is also equally shitty, in terms of its ability to filter out the other wavelengths. The differences with the industrial filters is very striking. The red filter is a little better, but there is still a lot of blue and violet within the response. It doesn't attempt to remove any infrared at all. I bought some cheap laser pointers, with a total budget of just $10. All of these lasers claim to have an output power of 100 milliwatts, but somehow I doubt that any of these devices can manage even half that power, but they are more than sufficient for my purposes. Okay, let's test this spectrometer with some lasers. The issue with lasers is that the radiant intensity is very high, so it can be difficult to not saturate the spectrometer. It requires a little care in aiming the beam. The main line from this violet laser is at 410 nanometers. It is a very narrow and intense line, but there are also peaks in the infrared at 820 nanometers, and a small green peak at 505. It looks like this device uses an infrared pumped, frequency doubling, second harmonic generator to create the 410 nanometers main line. If anyone knows where the green component is coming from, please let me know in the comments. For the red laser pointer, the situation is a lot more simple. There is just a strong line at 660 nanometers. The green laser, I know to be an infrared pumped device. Normally these are driven by a laser diode at 1064 nanometers. Here, the main line is at 532 nanometers, there is also some energy at 1064 nanometers, which is the infrared pumped diode wavelength. What I don't know, is where this small peak at 625 nanometers is coming from. Again, if anyone does, please feel free to let me know in the comments. In terms of a more blue-colored laser, I have a miniature laser engraver. This claims to be a 448 nanometers, 800 milliwatt device. It is quite hard to measure this as the beam can't be made to be stationary, and I am worried that it will damage my spectrometer. Here it is in action, engraving some details onto the side of this spectrometer itself. I guess I have kind of invalidated my guarantee by doing this, but what the hell. It took quite a while to catch this moving beam. The main line is indeed at 448 nanometers, but there is also a secondary line, in the infrared, at 896 nanometers. This is probably the pumping diode wavelength, and judging by the small relative amplitude, has been filtered to remove as much of this as possible. This tiny engraver is not a professional level product, but it does kind of work. This is a high-pressure sodium lamp. In the past, these were the principal form of street lighting. Today, they have mostly been replaced by more efficient LED lighting. This type of sodium lamp was a lot brighter, and more efficient than the incandescent lamps that they replaced. In some places, these lamps are still used, for example in large warehouses. The power supply for these lamps is fairly interesting. They need both a ballast inductance and an igniter system. The startup process is quite complex. These lamps contain some sodium metal in solid form that needs to be ionized, so this sodium needs to transition through 4 states of matter before the lamp will operate correctly. Here you can see the 589 nanometer sodium D line starting to become active, and the lamp begin to brighten. This is a very monochromatic light source. Because the Theremino software only performs a ratiometric measurement, you can see the infrared lines appear to get smaller. In fact, they are not changing very much. It is just the sodium D line that is becoming more intense. One of the consequences of this monochromatic illumination is that it becomes very difficult to determine colors. Take a look at this color swatch. It isn't until the white LED lighting is switched on that the actual colors become apparent. This type of lighting has a rather ethereal quality to it. I'm not sure if I have forgotten just how beautiful these lamps were, or if I just never appreciated them back in the day. In either case, I'm pretty pleased that I bought one for this project and got to use it at night. In the end, the lamp, the ballast, and the igniter, together, cost about $10, so well worth the money. Looking at the lamp in operation, with a thermal camera, it is pretty obvious why these lamps have become obsolete. They generate a lot of heat, and this is the main source of the energy losses for this type of lighting. The ballast also gets pretty hot too. In combination with the lifetime limitations, I can see why LEDs supplanted them. And if you are about to write in the comments about how sodium lights were better for seeing through fog, then please do me a favor and do a Google search on that first. As I also discovered, this is an urban myth. The physics just doesn't stack up. The fact that you can still buy yellow fog lamps shows just how pervasive this myth has become. I was browsing Taobao, and I found this thing. This is a deuterium arc lamp. Deuterium, as in heavy hydrogen. I knew instantly that I must own this thing, even if it cost me a kidney, and even though I didn't fully know what it did. In the end, this lamp, and the associated power supply, ended up costing just over $70. So not cheap, but still leaving me with both of my kidneys. This light source is used for spectroscopy, and it produces a continuous UV spectrum from 200 to 400 nanometers. This is ideal for finding the shortest wavelength that this spectrometer can operate at. I am going to need to be pretty cautious with this thing. Unlike the Mercury vapor arc lamps, which only has narrow lines of UV light, this thing delivers a continuous spectrum of UVA, UVB, and UVC radiation. Consequently, it delivers far more ultraviolet energy, even though the peak intensity is lower. The power supply is quite complex for this tube. It needs a source of electrons to be present before striking the arc. This is supplied from a tungsten filament. The filament needs to be active for about 20 seconds before striking the arc. But once the arc is struck, the filament can be switched off. This deuterium lamp really is as beautiful as it is dangerous. So, this is the moment of truth. We already know from the Mercury lamp measurements that the detection limit is somewhere between 254 and 365 nanometers. Immediately, some of the characteristic lines of a deuterium lamp become very clear. This is the deuterium alpha line, and here is the beta. And this is the Fulcher alpha band. And we can now see that this cheap spectrometer is sensitive from about 330 nanometers. Just to confirm that the emissions beyond this are not being blocked by the glass of the tube envelope, I will just check that UVC is present with this test strip. And indeed, UVC rays are present. I wanted to use this opportunity to test another filter I had lying around. This one is a bandpass from 305 to 375 nanometers. What I hadn't expected was that at around 500 nanometers, the filter becomes transparent again to longer wavelengths. Looking at the thermal camera, we can see that this tube releases a lot of heat. It isn't designed for continuous use, and in fact is only rated for 1000 hours of operation in total. I'm sure you have seen this type of thing before. It's a combined white light, UV light and laser. Here in China, they are often sold in stationery stores. These ones cost me $1.40 each, which is a ludicrously low price. What occurred to me is that 40 years ago, this thing would have been science fiction. 30 years ago, all of the technology inside this device was confined to advanced research labs. 20 years ago, something like this would have been 3 times the size, and had 2 zeros on the cost. And today, kids can buy this with their pocket money, for less than the price of a candy bar. Maybe I'm getting old, but I still find that to be pretty amazing. It might well be a piece of cheap crap, but it is also a pretty handy test source for a spectrometer like this. It is wonderfully ironic that I am able to test a dirt cheap spectrometer with an even cheaper, multi-spectral emitter. Even though this light source is a very simple device, it still has a few surprises up its sleeve. Like, why does this white LED have so much infrared content? As you can see, this is a pretty comprehensive test source. We have some UVA rays over here. The white and the UV LEDs have infrared peaks at 890 and 800 nanometers respectively. The red laser line is at 650 nanometers. If anyone knows where these infrared peaks are coming from, please do let me know in the comments. Fire might well be mankind's very first invention. It is our light of last resort. Most of us keep some way of making fire in reserve, just in case the power shuts down. It can be a source of danger, and a wild power that induces fear. Yet all of us, at one time or another, have stared in deep contemplation into its hypnotic dancing flames. The spectrum of this candle is pretty much how you might expect. It is almost a perfect black body source. The excited carbon particles glow brightly from the heat of combustion of the hydrocarbon fuel. The peak of the emission spectrum is almost perfectly centered on the transition between the visible and the infrared. This is why the candle flame has a distinctly orange hue. The small amount of shorter wavelength rays, particularly the blue colors, come from the heated, but as yet, unburnt fuel, glowing from the intense thermal radiation emanating from the combustion above it. When viewed with a thermal camera, we can see that the heat plume is many times bigger than the visible flame. Normally, for an electric light source, we would consider this thermal energy to be a waste product, an inefficiency to be minimized. But to our ancestors, the heat might have been more important to them than the light. Mankind's original light source, the sun, has some interesting spectral qualities, so I was keen to capture this. But I live in the tropical area of southern China, and we are now in the beginning of the monsoon season. Capturing the spectrum of the sun seems like such a simple task, but somehow I managed to finish all of the other experiments, and it was still raining. Day after day, I waited for the sun to appear. But it just rained, and this video was almost completed. And it rained, and rained, and rained, and rained, and rained, and rained, and rained. And then, it stopped. Quick as a flash, I grabbed my computer and the spectrometer, and went outside to marvel at the big ball of fire in the sky. And to capture that precious spectrum. And here is what all the fuss was about. The solar spectrum is very interesting. You can literally see the basic chemistry of our nearest star, and of our own atmosphere. A pure black body source would result in a nice continuous spectrum, but this has a lot of absorption lines. These are called Fraunhofer lines. These dips in the spectral response are due to absorption by specific elements within the sun, such as hydrogen and helium. You can even see some of the lighter metals being created in our local star by nuclear fusion right now. The Earth's atmosphere also impacts this spectra. The oxygen and the water vapor also give very clearly visible effects. So, not bad for a cheap spectrometer then. This is a DIY project, created by an enthusiast, for other enthusiasts to use. It is not a mass-produced, factory-refined product, and as such, it is pretty simple inside. The main part of this device is a FDM-printed chassis. This is the key component of the system. All of the main alignments and the optical path are defined by this 3D printed part. There is a camera module to capture the light rays after the diffraction grating. The camera module is based on the OmniVision OV2710 sensor, but this is the monochrome version. This means that it doesn't have the Bayer filter on the CMOS sensor, and so has a much wider spectral range than the color version. The light slit is part of the 3D printed chassis and is about 0.5 millimeter in width. Having made one of these things myself, I know some of the challenges. I am willing to bet that the creator of this device filled up a good many trash cans with 3D printed parts before getting all of the alignments to be perfect. And then, we have the diffraction grating, which is just made out of a DVD, but this one is frankly a rock star compared to my efforts.
Swagger down the street with your red lips and funky beat, you better.
I spent so many hours trying different ways to get a good quality diffraction grating from a DVD, and none of mine looked like this. And at the end of the day, that is exactly what I was paying for. And do I mind that this is not a factory-made product? Nope, not at all. The creator made it very clear in the details on Taobao that this was a DIY product, that it was 3D printed, and even that it used a diffraction grating made from a DVD. The main case is also 3D printed. Mine is pretty battered now. I have used it a lot and it has basically lived in my bag since I bought it. The box has been painted matte black inside, and threaded inserts have been used to allow the lid to be screwed tightly shut. And that is basically it for this teardown. It is often said that only a bad workman blames his tools. I am not one of those people who allows meaningless, generalized expressions to guide my judgment. But perhaps there is some grounds for agreement with that sentiment. For example, this is a really low-cost, DIY spectrometer. But with some understanding of the limitations, there is probably some really good science that can be done with it. In the making of this video, I have already learned an absolute ton of things that I didn't know before. I also hope that you have gleaned 1 or 2 gems of knowledge. Who knows, maybe one day, something you learned here will be the tie-break question at the local pub quiz, or maybe even in a bigger quiz. As a tool for learning, this is a great device. This isn't a lab-grade product, by any stretch of the imagination. That said, the spectral range is pretty damn good, the sensitivity and resolution are also much better than I would have expected. This won't replace even a $1,000 professional spectrometer, but it will give it a bloody good run for its money. This is a useful tool, and I fully intend to get as much use out of it as I can. Now, about how to buy this thing from outside of China. I am still working out the details with the creator, but we have a couple of options. I hope soon that I will be able to figure that part out, so be sure to subscribe if you are interested, and you will be notified of updates on this topic. Anyway, that is all I have for you today. I hope you enjoyed my little video, or at least found some parts of it interesting. If you want to see more of this kind of video, you could always press the subscribe button. This is not a commercial channel, nor will it ever be, so I can say what I want, and YouTube's algorithm can go and get f***ed. Thank you for your time.